Hello, and today we're going to be doing homework 2 part A. So there's 4 different parts for part A, so I'm going to describe them now, explain what I'm going to be doing, and then we will get to doing part 1. So for part 1, the goal is to derive a time-dependent heat diffusion equation for a uniform linear bar, assuming constant thermal diffusivity. For part 2, we're going to express the heat diffusion from part A1 as an algebraic equation via backward explicit differencing. For part 3, we're going to simulate the time-dependent response of a uniform bar initially at 50 C after its ends are raised and then maintained at 50 and 80 C respectively. We are then going to discretize the bar into 100 sections and show the simulated results for R equals alpha delta T over delta X squared equals 0.5 and 0.501 respectively. Then for part 4, we are going to be using von Neumann stability analysis to explain why the simulation results are unstable when R is set to larger than 0.5, which actually kind of gives away part 3. So what I'm going to do is I'm going to get on the board behind me, and we're going to derive part 1, part 2, we're then going to code in Google Colab for part 3, and then for number 4, we're going to derive again on the board behind me. For part 4, and maybe for part 1 and part 2, but specifically for part 4, this is a very long derivation. So I am going to make a lot of cuts and a lot of kind of abrupt edits. I'm going to need to double check my work, and I don't want to carry anything through that's going to be wrong, especially if we're going to be using these values throughout the entire derivation. So after this, you should see me starting to derive part A1. Hello, this is going to be homework 1. This is going to be homework 2, part A of part 1. And what we need to do is we're going to derive an equation for a uniform bar, meaning that its constant conductivity is constant throughout, or the thermal diffusivity is constant throughout. And we want to calculate a temperature for that system. And what I've done here is write down a few of our notes. We have Tc on one side of the bar and Th on the other, along with a section here, which I am going to call x prime, and we're going to call this dx. We also have an equation that's pretty well known as Q equals K times A over delta T over dx, which is our thermal conductivity times the area multiplied by the gradient in temperature over the width or the distance. And our first step is we need to apply our equation to the system before we can start working on an energy balance. And what we are going to do is we're going to start with x prime. So we are going to have Q equals K times area, given by itself, times dt over dx. And we're going to do this with respect of x prime, which is tiny. You probably can't see it, but it's here. But one thing we actually have to take into account is that our Q is going to be negative. And so we need to make our K negative here. And the reason our Q is negative, as we're applying this at x equals x prime, as this x is giving our location, and x prime is giving our location. And the reason our value is going to be negative is due to the fact that here, I'm going to make a graph, where x is our position on the bottom, and our temperature is over here. So we have TH up here, and then we have TC. So if we have TC, and how do we know that temperature goes? Temperature goes from hot to cold. So that means we know our temperature is going to be going this way. It's going to be working its way down the system. And because of that, we know that because this is a positive slope, this would be, if it was going in our direction to our right, it would be a positive slope, and we follow that and it would be a positive value. But because our temperature is going in the opposite direction, of x, that is actually going to lead us with a negative value. So we have our Q, but now we also need to basically write for our Q, we have our x prime, but we also need to write for our dx. So we have Q dx with respect to dx equals negative K times A, making sure you can still see me, and I'm not going to be tripping over my charger. If it happens, it happens. QA times dt over dx with respect to x, our position, equals x prime plus dx. And this is because we have our x prime, you'd be saying from here to here, and then also we need to add to our dx. This is what this distance here is. So now that we have our numbers, or our values for our equations, we can now plug it into an energy balance. And I'm going to move these two equations over to under our equation tree, and then I'm going to pause while I do this, and then we can start doing our energy balance and derive this equation. All right, as you can see, I moved our equations over to the board and over to this side of the board while I cleared our middle, and we can start our energy balance. So what we're going to start with is, this is a change in temperature problem. So we have dt, we also have over time, of course. We also are going to have what's going to be changing. So we are going to have C in there. C is joules per kilogram Kelvin. And now we need to figure out how to get kilograms. So to get kilograms, let me move this. We want to get the mass. And to get the mass, we need our density times our volume. So our density of this system, which is, so if we can do, I'll just bring this down. So we have joules per kilogram Kelvin times kilograms per meter cubed. But now we need to get rid of meter cubed. And to get rid of meter cubed for our bar, we need a volume inside of our section. So we're going to multiply by the cross-sectional area multiplied by dx, or our width, because this gives us meters squared times meters. So we have kilograms per meter squared, kilograms per meters cubed, multiplied by meters cubed, giving us only kilograms. Then we have joules per kilogram Kelvin, which those kilograms cancel, so we have joules per Kelvin. Then we have our dt, which is in terms of temperature, or Kelvin, obviously, which then leaves us with joules over time, so our joules per second. So now, this is our change. We need to figure out what we're going to put over here. So what we're going to look is, we're going to put something right here, where this is essentially our cross-section. And if you can remember from original, we have our temperature C, our temperature H, so our colder temperature, but our hotter temperature. However, because it's closer to temperature C, and this entire bar outside of these points at original is kept at 20 degrees Celsius, we're going to have energy moving in and energy moving out, which is exactly what we're going to do over here. So we have in minus out. So our in is going to be negative Ka dt over dx for x prime. Well, the energy leaving is going to be minus negative Ka dt over dx for x equals x prime plus dx. Make sure you can still see. And this is essentially our energy balance. With my great handwriting, and probably too tiny for you to see. But now we need to basically cancel a few things, or moving a few things around. So first, we notice that this double subtraction is going to be a plus, and then we can get rid of this negative sign. And we also need to figure out what's changing in the system. We know that our density is not going to change. Our area is definitely not going to change. Either this is a dx. This kind of looks like a dt. I'm sorry, let me rewrite that. Yes, we know our density, our area, and our dx. These are not going to change. Neither is our c, and neither is our c. So we can take these out of our system. And we end up getting, if we take these out, we're going to do rho A dx. We're going to take these out first. We have area, we know it's going to cancel throughout everything. So we can cancel area, cancel area, cancel area, right? And our k's are going to then combine, equal, so we're going to have, let's just put dt over dt equals our k value, where the negative is going to disappear, times over rho c, right, because these are the same system essentially. We're also going to take up c now. I was a little lost, but found my way. So we have a, so we have rho, dx, and c. So we're going to take across rho and c first. And because we have 2 dt's over dx, meaning if we try to divide across by a dx to our already dt, we end up getting our second derivative. So we have d squared t all over dx squared. And that's by dividing this across, or these values. So you end up getting dt over dt, so the change in temperature over time, equals K over rho C, our thermal conductivity divided by our specific heat and density, times our second derivative of temperature over position. And this is actually our equation for how we solve this problem. So in the next part, I am going to be, what am I going to be? We're going to be solving for, once we discretize it, I believe is the correct term, or differentiate. And I'm going to erase the board and we will get right back to it. Welcome back to our homework 2A. This is going to be part 2, where I butchered at the end of the last part. We are going to express this equation here, which we derived last time in an algebraic form. So one thing I didn't mention was that we use alpha to designate K over rho C, just because it's easier and they're all constant. So we're basically just combining the constants into one constant, so it's easier to write. So another thing I need to bring your attention to is this is a different bar. It's the same bar, I just put it into sections, and there's 2 different things we need to kind of talk about. So first we need to talk about step sizes. So when we're talking about time and position, we are going to use the notation such as we use up in this T up here, where time is J is position, so it could be any position here, it could be 4, it could be 3, depending on what J is. And then it's also N, where N is the time, because just knowing the position isn't enough. We need to know at what time and what position the temperature is. Those are both really dependent on each other. As shown in this equation where you have time, temperature, and position throughout the entire equation. So we need to talk about step sizes. So our total temperature, or our total time, is going to be our step size, so T times N, which is the amount of, basically the amount of steps we want to take. It's going to be the same for x, where x equals delta x times n. And granted, these are most likely going to be different amounts of step sizes. We don't want to use the exact amount of step sizes for time as we want to do for position. It really depends on what you want to do. But this is something we need to write down. But now, we need to basically write this equation in this term. So our first one is dt over temperature over time. So we're going to have T, so temperature is times N plus 1 minus Tn, these are both going to be at the same position, all over dt. And instead of dt, we're going to start writing it as delta t. Same with delta x. Just because it's easier, it's in algebraic form. So we have, because this is a change in time, we have basically the next time minus our current time divided by our, that's x, this should be delta t, I'm so sorry, divided by our position. We are doing a derivative by hand, we're finding the slope. Equals, so right here off the bat, delta x. We know it's going to be, at the bottom, is going to be a delta x, which in our place is or dx, which is going to be a delta x for us. So now that, but for this, it's position. So we have t, everything here is going to be tn. Tn of j plus 1 minus tj all over delta x. As this is a second derivative, we're going to have to do this twice. Minus Tn of j minus Tj minus 1. And this is also going to be over delta x. So this is what our equation looks like. We have our change in temperature over time, and then we have we're using the temperature in terms of position over here. So what this actually ends up breaking into is, we're going to need to do a little bit of algebra, as our glorious Professor Carlos Coe says, we need to massage it a little bit. We are going to take, oh, I forgot a very important part. We forgot our alpha right in the front. So we are going to, this is going to break down, and then we're also going to break down this, because what we really only end up wanting is this guy right here. We want to know our next time, or at this current position, what's our next time? Jesus, that does not make sense. At our next time, what is the temperature at the same position? That's what we want. So we're going to multiply this across, right? And then we're going to add this across. So we're going to go over here and hope we have enough room. T, J, and then N plus 1 equals, and because we have, this is the same term as it is over here, we have, what are we going to do? Yep. We have alpha, it's alpha times delta t all over delta x squared, which is our constant in the front. Then we're going to multiply this by, so we have n plus 1, so we're going to do t n, and this is j plus 1, minus, because we have negative, so plus negative, and then we're going to add this cross, minus 2 t j n plus t j minus 1. And in this form, because everything right here is a constant, it's known. We know all these values. Well, over here, this is in an algebraic form. We can actually plug into something and solve. So now that we have everything, we can basically calculate our temperature at any given time and any given position based on this equation, which is honestly pretty interesting. I never thought of it this way, and I actually lost an n here. So what we're going to do next is we're going to actually code out this in Google Colab, and we're going to see how a computer, and if a computer can handle the second derivative and how it looks on a plot. So it turns out I actually lost a value. I actually lost this one, this number when I was actually carrying it across, because we have a negative here, and then this is a minus a positive, so it'll be negative plus negative, which is how we get this negative 2. So what we actually need to do is add this part to the end. So I usually, in almost all the derivations, we put it in front, but I don't have the space for that, and I don't feel like erasing. So we're going to add it at the end. T, J, N. And the difference is this doesn't have the bounds, or this isn't multiplied by our alpha, delta t, delta x squared, such as this term is. So we just need to take it out of the equation, take it to the outside of all of this mess, and we can either put it in the front or the back. And in this time, we're going to leave it in the back. But as I said, we're going to start coding it out, and we're going to see what happens. All right, now it's time to code out the equation we just created. So first we need to create our array for, let's see, np dot full will be n comma 20. I hope that actually works. Fill, it's fill. I get those mixed up. Or not. Let's see, F. Let's see. Full shape fill value. The N. Well, that's what I want. But anyways, then we're going to do our T. And because it's going to be an array, we want our first value. Actually, our first value is 0. No. I think our first value is going to be 50. If we look at maintain it, the ends are raised. So our array, our different temperatures, we have our start and our end, right? And we have T dash -1 is going to be 80. It's 80. And then we want to do our position. It's going to be np.arrange. np full. I don't understand why that doesn't work. Function object is not scriptable. Okay. Still value. Function is not a, what if it's just full? NP, okay, it's got to be a numpy. And okay, after that, so now we would want to make our graph. We have to do fig equals make subplots, and then we want to do fig dot add underscore scatter. We do x equals position, which is what I need to fix this, because what we're going to do is we're going to arrange our values for x. Position, we're going to do y equals t. Oh man, I'm not doing too hot right now. Y equals t, and the next one is mode equals lines. Probably isn't right. And then we're going to do name equals f dash. We're going to name it something. I'm drawing a blank here. And alright, now we want to do a for loop so we can basically add all of our values. So for I, it's basically want to do like 5,000. And then we just want to keep adding our values. And like what we want to do is add our equation that we created in here. But I'm kind of concerned why fill isn't working. So before we get to that, I'm going to double check why that's not correct and what I'm doing wrong. So I'm pretty sure I had tried np.full, but it actually worked. And so now what we want to go down here is do arrange-n. So this is just going to basically create our x values. And then what we want to do is create our first plot at 0, which is why we're creating this. And then we're going to do for I in range of 5,000, or I think 50,000. We want to do, let's see, we'll do that. Our temperature, and it's going to be 1, 2, comma, -1, I think. Like this is going to equal, I think it might just be 1 on, but we will get there. Don't count our chickens. We're going to do temperature -1 to 1. This is the value I put at the end, plus r times, let's see, that's going to be, I wrote down a little bit here. So our n plus 1 or n plus r, and it's tj. So it's going to be, I'm going to do t dash 2 and on minus 2 times t, we're going to do -1 to 1 plus t to then, I think it's going to be that to -2, or it might, let's just do -2 on. I don't think this is right, because what I end up doing is, this is our t, I actually have this written behind me, we have our tj n plus 1 equals our tn, so this would be the same, plus r times our t value, then j plus 1 minus t, just j, plus t j minus 1. So let's see, I'm going to do, yep. That just worked. That, quite literally, it was just working. Maybe another error superseded it, but what if I do parentheses, which wouldn't make sense because it's an array. Yeah, because we want to do this as an array, which tracks, but it was just working. So then after we do that, we either want to create our figures for this, or we want to add another thing. So for example, we do like for percent 1,000 are not equal to 0, we need to create a name. What this would essentially be doing is we're going to actually create our plots at the different I values for 1,000, I believe. Basically, and if it's multitudes of 10, because it would be 0. And if we're doing 1,000, that'd be like 50, which would seem good enough. We would then do fig dot add underscore scatter x equals position, y equals temperature, mode equals lines. That we're gonna do name's gotta be equal f. I'm gonna do that. I'm gonna be I. All right. It's an invalid syntax. So I'm going to double check this again. And for some reason this is causing an error sometimes, other times it isn't, and I'm not sure why, but I'm going to double check the code, double check this syntax, because right now I know the goal is we can make different plots. So we have our 0 value, right? This is for 0. Now we want to create our different iterations for this right here. We also don't want to create a million iterations where it just covers up the entire plot. We want to kind of divide it down by a certain amount. So for every 1,000, essentially, of 50,000, we get 50 plots. 50 lines should be more than enough to show us what we want to see. All right, I found an issue again. This would not be a for loop, it would be an if it's an iteration of 1,000. And while looking through NumPy, it says this should be parentheses. So we will hope and pray that that works. I arrange -1. We actually need to change that because it's supposed to be the same, I think. And then this would be 2 dash. And this is the wrong order. -1 to -1, and I don't understand how this is invalid syntax. Maybe like that. Percent sign, which I think is the right sign. Because what we're doing is like if it's an iteration of 1,000, we also want to index this value because we're calling on I, so we need to figure out what I value it is. X position, light mode lines, but this is invalid syntax. I might need to create the name, but if it's divisible by, this shouldn't be wrong. But I'll be right back again to see if this is right. All right, this mistake was actually a pretty bad one on me. It's if, but we're not calling anything. If I is an iteration of 1,000, and also I spelled a range wrong. So if we do that, and then we do figure, which all things should create a graph. And look, it's perfect. What we can see is from 50 to 80 up here. And the temperatures all started at 20. right? As you can see, at 0, it's all 20 from there to there, and it goes down and up. Like the temperatures were going across, it's obviously more steep at the hotter side, as it has more energy to give. And the usage, you can see, goes from 1,000 to 2,000 to 3,000 to 4,000. It's essentially creating its slope over time as the temperatures even out. I don't want to say steady state, but that's essentially what they're creating. And then at that point, all of these numbers are just very similar at the end of the day up here. And so again, my issue was, the combination of all my issues was, didn't do NP full, even though it worked and then it didn't. I spelled a range, which was also causing an issue. I didn't realize, I messed up my indexing. This was, I messed up my negative ones and ones here. And then I messed up my I percentage, or my I, because I just didn't realize it. It's ironic. But now that we have our graph for 0.5, the homework says to try it at r equals 0.5 and r equals 0.51. So let's do, that's what 0.5 looks like, 0.51. And it breaks, interestingly enough. Like, you go 0, it's only, don't worry, it's only up to 10 to the 71th value. Let's see what happens if we, 1,000, 2,000, 4,000. It starts ramping up the excess. It goes up to 6 million, 200 billion, 200 trillion, and then we get out of everywhere. But yeah, that's exactly, turns out it just breaks if it goes above 0.5, which we are actually going to explain, and I'm going to derive on the board behind me using the von Neumann stability analysis in the next part. So thank you for watching. All right, now that we have coded everything out, we need to do the stability von Neumann method. But before we do that method, we need to actually see if this equation we have up here, t equals exp to the negative alpha kt times exp to ikx is actually a answer, or is actually solves for t. And it can't just solve for t. It needs to solve for t at specific points. Basically, this equation needs to solve for t at 0 time, at position 0, at any time the far side of the bar is 50, while the other side is 80, and that any place in between that at time 0 equals 20. So we have a very specific equation. And we also are going to have to use our equation we had solved before to plug into this. So first, something we also have to know is that we have I in here. I is the imaginary number that's negative square root of 1. So what we're going to do is we're going to essentially use this and kind of combine them and see if it actually is a solution. So we have dt over dt. So we basically, with respect to temperature, we take the derivative of this. So you end up getting negative alpha kt equals, and then we are going to then take the derivative of this fun thing with respect of x equals the ikt, we have alpha, then we do d over dt. I'm going to write this bigger. So we have negative alpha kt, ugly looking, but it's there, equals alpha. And now we're going to do d dt, because it's still going to have to be taken again because it's a double derivative. Another thing, and before I get any further, I am going to write this expression as t. That's what this expression is. I don't want to keep writing it, and as I said, it's for a very specific k value, because k changes with time, or temperature. So essentially what this is a temperature for a specific k value, but I'm going to assume, or just write it all the way through as t, because I don't like writing subscripts and they're hard to see on the video. And then, so it's d dt, so we're going to have ikt and then we're going to take it again sorry for the abrupt cutoff. I was going through and realized my numbers weren't making sense. And I actually forgot to put this k value up here squared, which actually means this value is a squared k right here. And so we have alpha d dt IKT, and what we end up getting is, the first row we had IK, or we had IKT, when we take the derivative, we get IK. So we end up getting negative alpha k squared t equals alpha I k t times I k, which I'm going to do the math over here real quick. So we end up getting alpha I squared times k squared. Oh, I just tripped over my charger, my bad. Times t. And something about I is as we said, I is square root of negative 1. So I squared is just negative 1. It's just going to turn this term negative. So we end up getting negative alpha k squared t equals negative alpha k squared t. So what this solution is telling you is that this equation solves our problem. We could have a constant up front. For example, we're just going to call it ck. But even if you have a constant, it still ends up solving our problem where it hits all of these points that we specifically specified in the equation. It solves it for us. So now that we know this equation works, we can actually start evaluating it using the von Neumann method and figure out what is causing the stability issues in our in our algorithm or in our code. So what I'm going to do is I'm going to erase this, and then I'm going to set us up for the next part of the von Neumann method. All right, I've erased the board, and I've actually added a few more equations on the right. I'll go over them real quick. So I've added just a TNJ, which is kind of what we did in part B, just as a reminder. Also, this is Euler, but e to the ix equals cos x plus I sine x, just a reminder. And then our step sizes, we're also basically going to pull them back just as a reminder again. So what we want to do is we basically want to write this, or before we get into that, something that you need to kind of remind ourselves is that this doesn't solve exactly for temperature, it's a summation. So like technically, we're solving for a summation of, I believe, J. And we're solving for our specific temperature for a specific K, and we're summing it up. But again, that's a lot to write, so we'll keep it as T, not even TK, just because that's a lot to write. So what we're first going to do is we're going to rewrite this in first these terms over here as we have time and position, and then we're going to solve. We're going to do J plus 1 and J minus 1 to kind of get these values back again for this equation, which is exactly what we did for B, but with a different equation. So we're going to rewrite this as T equals EXP to the negative alpha k squared, and then we're going to do delta T subscript n, because n is time in our T and J, times the EXP through I, K, and then delta X, and we're going to call that delta X J. So what now we want to solve for is this is essentially TNJ. That's actually the opposite notation. That's ugly, that's my bad. TJN. This is our base. This is our base equation. Can you see? All right, it's tiny, but I will write bigger down below. So now we want to do TJ plus 1. And what that is going to be is first we're going to call this, again, TJN. TJN. Keep that the same because I'm not rewriting that again. Multiplied by this value up here, because this is our x. If we're adding our x value, we're going to have to bring our x term down again. So times, we're going to write this in terms of e now. E to the I, K, W, X. ik delta x. I don't know where that w came from. That's scary. And now, what if we do tj minus 1? We still have equals tnj multiplied by e to the negative ik delta x. And that's because this is an e, the Euler's constant, whenever you're going to subtract and you make it a negative, it's the same thing as subtracting that value away from it. Because if it's positive, negative, exponential, it's the same thing. So now what we're going to end up doing, which I don't think I actually have the space on this board right now, even if I wrote small, is if you remember when we kind of factored out, or when we did our equation, we wrote out as an algebraic form for part B when we did our algebraic form so we can plug it in. We did over, delta x minus over delta x all over delta x, and we ended up getting an r value, which is how we got this value up here. So what I'm gonna end up doing is I'm going to erase this board to give us room, and then I actually think I'm going to move these terms over here so I have more room, but I still want to remember these values. And then we're going to do it all over again, but for this specific equation. And that's because this is how we're going to do Newman's, or von Neumann's stability. Is we want to get it into an algebraic form that we can actually solve for a numerical answer. So I'm going to erase, I'm going to move, and I will be right back. All right, now that I have space, I'm going to skip the steps that we did in part B, where what I just explained right at the end of the last clip. So we're going to have tj n plus 1 equals tj n, ugly looking j, and I made it worse. So we're gonna fix that. Here I'm gonna be mad. J plus r times, it's going to be tj n times e to the negative, e to the, let's see, it was I k delta x minus 2 t j n to the plus t j n times e to the negative I k delta x. So we're going to factor out a tjn, and we get this beautiful looking thing right here, tjn. We're going to get 1 plus r, and we're going to have, I'm just going to call this e to a positive. I don't care at this point. Minus 2 plus e to a negative. So e, I wrote this over here. E to the ix, which we have an extra term, which doesn't change anything, equals cosine x plus I sine x. So what we get up here is we get e to the ik delta x plus e to the negative ikx. So what we end up getting over here is we would get, so we're going to do e to the positive plus e to the minus. So we end up getting, let's see, cos plus I sine x plus cos minus I sine x. So this term ends up equaling 2 cos, this is actually going to be I k, I don't think, no, not I, but k delta x. So we have t to the n plus 1 j equals t n j, then 1 plus r cos to, oh, my bad, 1 plus r Then we're going to have another parentheses to the negative 2 cos k delta x. And we're going to see if I'm missing a term here. Because I feel like I am missing a term. But now that we have this number, we can actually convert this into an algebraic form. And, oh, I know what I missed. So because of these values in the 2, what I'm thinking happens, turns into a positive, and we end up getting 2 cos x minus 2 at the end, because we have I here, and I believe that I turns us to yes, I'm agreeing with myself. So we end up getting this term here, tj to the n plus 1 equals tnj multiplied by everything inside is going to be 1 plus r times 2 cos k delta x minus 2. And now that we have this, we can actually convert this into a algebraic form that we can work with and we can actually convert. So what I'm going to be doing is I'm going to erase probably everything. I'm going to move this bad boy up here so we can start doing actual algebra and we can solve using von Neumann's stability method. So as you can see, I erased the board and I rewrote our equation. So the first thing we're going to do is factor out of 2. So this is going to do t, and my writing is going to get a lot worse from here on out because my arm is tired, but I will still enunciate everything I'm doing. So Tn, n plus 1, n plus 1 equals T and J, then we have 1 plus 2r cos delta x times k, parentheses, minus 1, parentheses, parentheses. So something you might be able to notice is that the max value of a cosine is 1, right? So if we say this is 1, we subtract that's 0, and then this is 1. So this means this term, the max value it's going to get is going to be, it can be 1. And if we know that x value is 1 in absolute value wise, because we know this won't, 1, this is going to basically reverberate across itself, and this might, what we think is causing the shooting up issue. So we are going to actually, because we know the max value, we're going to set it to absolute value. That way we can start to solve. So absolute value is going to be negative 1. We have 1 plus 2r cosine delta x times k. I know my writing is immaculate. Minus 1. And it's going to be 1. So we're going to subtract this 1 out. So what we're going to do is we're going to take this 1 out. So we're going to erase that. We're going to make this negative 2. And we're going to make this 0 because I am tired of rewriting. So now let's look at it again. If we know this value is 1, right? We know the max value is 1. Minus 1 is 0. So we know it's never going to be greater than 0. So we can actually get rid of this term because we know the max, let's say if we look at the max value, it dies. So we can get rid of it. So we're going to now get rid of this term. And we can divide across by 2. So we end up getting negative 1 is less than or equal to r cosine delta x times k minus 1. I think I did something wrong with my math. I'm going to be right back. I'm going to double check everything and make sure it all adds up. All right, the math was right. I just got a little ahead of myself and got lost. So now that we have negative 1 is less than or equal to or r cosine delta x of k minus 1 is greater than or equal to 1, we want to look at the max value again. So it's, again, the max value of cosine is going to be 1 or 0, right? But if we look on the other side, the max value can also be -1. So if we decide this is -1, we end up, you can call this -1 minus 1 equals -2. We have -1 is less than or equal to -2r. And if we divide by -2, we also remember we have to flip the sign. So we get 0.5 is greater or equal to r. So what this is saying is r cannot be greater than 0.5 using the von Neumann analysis. If it is, essentially it creates, I think you saw, and I was coding and I looked at the 1,000, 2,000, it didn't start off really big, but after each 1,000 iterations, it got exponentially bigger, which is because if it's bigger than 0.5, its value essentially reverberates back and forth. It just causes this number to increase at an exponential rate. I believe it got all the way up to 0.78, or to the 78th power, which is insane. So by using the von Neumann method, we have found that the max value of r cannot be more than 0.5. And I think that's going to be, all the homework. I think it explained the whole thing. So thank you for watching.